degradation, and defluorination of perfluorooctane sulfonate, PFOS, in water using hydrodynamic cavitation. Per- and polyfluoroalkyl substances, PFAS, particularly perfluorooctane sulfonate, PFOS, are highly persistent environmental contaminants due to the exceptional strength of the carbon-fluorine bond. The carbon-fluorine bond is the strongest single bond in organic chemistry, with a bond dissociation energy, BDE, of approximately 485 to 488 kilojoules per mole, making it highly robust, chemically inert, and thermally stable. In comparison, carbon-carbon single bond strength is 347 kilojoules per mole. Conventional treatment methods are largely ineffective or energy-intensive, necessitating the development of scalable and efficient degradation technologies. This video presents hydrodynamic cavitation, HC, as a promising approach for PFOS degradation and defluorination in aqueous systems based on a recent article published by a research group in Germany. The study evaluates degradation kinetics, fluoride release, and energy efficiency under controlled cavitation conditions, highlighting the potential of HC for sustainable PFAS remediation. PFAS constitute a diverse class of synthetic fluorochemicals widely used for their hydrophobicity, oleophobicity, and chemical stability. However, these same properties render them resistant to environmental degradation, leading to widespread contamination of water systems and bioaccumulation in living organisms. PFOS, one of the most studied PFAS, has been associated with adverse health effects, including immune dysfunction, endocrine disruption, and carcinogenicity. Conventional wastewater treatment processes are ineffective in removing PFAS, often resulting in secondary contamination. Existing destruction methods, such as incineration, pyrolysis, and advanced oxidation processes, face challenges related to high energy demand, incomplete mineralization, and scalability. Consequently, alternative approaches capable of achieving efficient degradation and defluorination are urgently required. Hydrodynamic cavitation mechanism. Hydrodynamic cavitation involves the formation, growth, and collapse of vapor bubbles in a fluid due to localized pressure fluctuations. In orifice-based HC systems, rapid pressure drops induce cavitation, followed by violent bubble implosion. This process generates extreme localized conditions, including transient temperatures exceeding 5,000 degrees Celsius and pressures of several hundred atmospheres. These conditions produce reactive species such as hydroxyl radicals, hydrogen radicals, and solvated electrons, which contribute to contaminant degradation. PFOS molecules preferentially accumulate at the bubble-liquid interface due to their amphiphilic nature. During cavitation, degradation occurs primarily through pyrolytic cleavage at the interface and within the bubble, where high heat and pressure enable the breaking of carbon-fluorine bonds. Subsequent reactions involving reactive radicals facilitate further breakdown of intermediate species, ultimately leading to mineralization and release of fluoride ions. Experimental parameters and evaluation metrics. The HC system was operated under strong cavitation conditions, characterized by a cavitation number, CV, of approximately 0.032 and a turbulent flow regime, RE, approximately 1.57 times 10 to the power of 4. These conditions promote intense bubble collapse and efficient energy transfer. PFOS degradation efficiency was determined by monitoring concentration changes over time, while defluorination was quantified through fluoride ion release and mass balance analysis. Degradation kinetics followed a first-order model, enabling the determination of rate constants and comparison across operational conditions. Key performance metrics included electrical energy per order, EEO, energy yield, milligrams per kilowatt hours, and total energy input, kilowatt-hours per cubic meter, providing a basis for assessing process efficiency and scalability. Under optimized HC conditions, PFOS degradation of up to 37% and defluorination of approximately 20% were achieved. The release of fluoride ions confirmed partial mineralization of PFOS, indicating effective cleavage of carbon-fluorine bonds rather than mere transformation into stable intermediates. Degradation proceeded via stepwise chain shortening, producing lower concentrations of short-chain PFAS as transient intermediates. Higher initial PFOS concentrations, for example 5 mg per liter, enabled more reliable quantification of fluoride release and mass balance closure, whereas lower concentrations were influenced by sorption and interfacial effects. Energy efficiency analysis showed EEO values ranging from 7 to 598 kilowatt-hours per cubic meter per order, and energy yields between 17 and 286 milligrams per kilowatt-hours, demonstrating competitive performance relative to other advanced treatment methods. The cavitation-driven process was strongly influenced by operational parameters such as pressure, flow rate, and number of passes through the reactor. Increased recirculation enhanced cumulative exposure to cavitation, thereby improving degradation efficiency. The results confirm that PFOS molecules reaching the cavitation zone undergo near-complete thermal decomposition, followed by radical-mediated oxidation of intermediate products. Process integration and scalability. HC offers several advantages over acoustic cavitation and other advanced treatment technologies, including lower operational costs, simpler reactor design, and improved scalability. However, treatment efficiency at environmentally relevant trace concentrations remains a challenge. To address this, integration with concentration techniques such as adsorption, membrane filtration, or foam fractionation is recommended. In such hybrid systems, PFAS can be concentrated and subsequently degraded on-site using HC, minimizing secondary waste generation and eliminating the need for high-temperature incineration. Further performance enhancements may be achieved by introducing non-condensable gases, such as argon or oxygen, which influence bubble dynamics and increase local heat, and by optimizing reactor geometry to intensify cavitation effects. In conclusion, hydrodynamic cavitation represents a viable, non-thermal, and scalable technology for the degradation and defluorination of PFOS in water. The process enables effective carbon-fluorine bond cleavage through localized extreme temperature generated during bubble collapse, resulting in partial mineralization and fluoride release. While current degradation efficiencies indicate the need for further optimization, HC demonstrates significant potential as part of integrated treatment systems for PFAS remediation. Continued advancements in reactor design, operational conditions, and hybrid process integration are essential to enable large-scale implementation and address the global challenge of PFAS contamination.